All right, let's dive in. Today, we're talking about the invisible rules that run the world. We're going to explore the fundamental principles of forces and motion, the very things that dictate how and why everything around us moves. So, what do a falling apple, a baseball in midair, and a pendulum and a clock all have in common? It sounds kind of like a riddle, right? Well, the answer is physics. All of these things, as different as they seem, are actually governed by the very same elegant set of rules. And in this explainer, we're going to pull back the curtain and see how it all works.
So let's start with the most basic motion there is, falling. It's something we see every single day, but as you're about to find out, there's a little more to it than just what goes up must come down.
You know, in a perfect physics textbook world, an object is in what we call free fall. That means only gravity is pulling on it, nothing else. But here, on planet Earth, that's not how it works. Our stuff falls through the air, and air, believe it or not, is a fluid. And that fluid pushes back. It creates a kind of friction, a resistance that fights against the object's motion. And we can actually describe that pushback with some real precision. For little spheres, there's a principle called Stokes' law that defines this drag force. It all depends on the object's size, how fast it's going, and what the source material calls the coefficiente di viscosità, which is really just a fancy way of saying how sticky the fluid is. Just picture a marble falling through honey versus that same marble falling through the air. That's viscosity in action. Okay, so falling straight down, that makes sense. But what happens when we mess with that? What if we don't let the object just fall, but instead we make it move along a slope? Right, on an inclined plane, motion becomes more of a negotiation between forces. Gravity, of course, is still pulling straight down towards the center of the Earth. But now, the plane itself is pushing back with a support force. The source calls this the reazione vincolare. The result of this tug-of-war is that only a part of gravity's force actually pulls the object down the slope. And that gives us a nice, smooth, controlled acceleration. Okay, so we've covered going straight down and going down at an angle. Now for the really fun part. Let's give our object a good sideways push and watch it fly. Welcome to the world of projectile motion. The secret to understanding how a projectile moves is to realize it's actually two different stories happening at the exact same time. Seriously. First, you have the horizontal story. If we ignore air resistance for a second, there's no force pushing or pulling it sideways, so it just coasts along at a steady speed. Then, at the same time, you have the vertical story. Here, gravity is in charge, pulling it down with a constant acceleration. The object is doing both of these things at once. And when you combine those two simple motions, you get that beautiful, perfect arc. And because we understand both parts, we can calculate everything about its journey. Its gittata, which is its total range, its quota massima, the highest point it reaches, and its tempo di volo, the total time it spends in the air. It's amazing, really. Two simple movements creating one complex path. All right, we've handled straight lines and we've handled parabolic curves. But what about just going around in circles? Let's take a look at the physics of a steady, constant turn. This is what we call uniform circular motion. Now, here is the absolute key. The object's speed is constant, let's say 10 miles an hour, but its velocity is not, because velocity includes direction. And in a circle, your direction is always changing. And if your velocity is changing, that means there has to be an acceleration. And where there's acceleration, there's always a force. And that force has a special name, centripetal force. But, and this is so important, this is not some brand new magical force that just appears out of thin air. No, it's the net result of other real forces that are already there. It could be the tension in a string you're swinging, or the force of gravity keeping a satellite in orbit. It's simply the sum of all the forces that are pointing toward the center of the circle, constantly yanking the object away from the straight line it wants to travel in. So, we've gone from falling, to flying, to spinning in circles. Let's shift gears one last time and look at a completely different kind of movement, the repetitive back-and-forth rhythm of oscillations. The two classic examples you always hear about are a mass on a spring, just bouncing up and down, and a pendulum swinging from side to side. Now, they look totally different, but as we're about to see, they are deeply,
deeply connected.
For the spring, the whole thing is driven by a simple rule called Hooke's law. All it says is that the more you stretch or compress a spring away from its comfy resting position, the harder it tries to pull or push back to get there. It's this constant restoring force that drives the whole back and forth motion. Now over to the pendulum. This is where things get really elegant, but there's one condition. The real magic only happens when the swings are small. For these piccole oscillazioni, as the source calls them, something absolutely incredible takes place. This is the principle of isochronism, which literally means same time. It means that for small swings, the time it takes to complete one full back and forth cycle, its period, is always the same. It doesn't matter if the swing is a little wide or if it's tiny. The timing is constant. You could immediately see why this was a total game changer for making clocks, right? It meant your pendulum clock would keep perfect time, even as the mechanism wound down and the swings got smaller. So let's just stop and think about this for a second. We have a mass on a spring, driven by a stretching force, and we have a pendulum, driven by gravity and tension. Two completely different physical setups, and yet they both dance to the exact same beat. The underlying mathematical rhythm of their motion is identical.
And that beautiful, unifying rhythm has a name: simple harmonic motion, or moto armonico. It's the purest form of oscillation, the signature pattern you find anytime there's a restoring force at play. It's just a stunning example of how one single elegant idea in math can describe so many different things in the real world. So from falling apples to flying balls to swinging clocks, what we've seen today is that just a handful of simple rules, gravity, support forces, restoring forces, can give rise to all the incredible variety and complexity of motion that we see all around us. It really makes you wonder, doesn't it? What other hidden patterns are out there, orchestrating the beauty of our world, just waiting to be explained?